So let's try some practice problems with motion along a line. So the problem says a particle moves along a line so that its position at any time t is greater than or equal to 0 is given by the function s of t is equal to t cubed minus 6t squared plus 8t plus 2, where s is measured in meters and t is measured in seconds. So for A says find the instantaneous velocity at any time t. So here we use the equation for instantaneous velocity, which we have just learned. So Vt equals ds over dt, which equals the limit as change in t approaches 0 of f of t plus change in t minus f of t over the change in time. Now if we see here, we already learned that instantaneous velocity is the first derivative of this position equation, and we are given this position equation. So what we need to do is find the first derivative of this position equation to get our instantaneous velocity equation. So to find the first derivative, we take this first part, and with the laws of derivatives, we multiply and we get 3t squared, and then we take the second part minus 12t, since we multiply the exponent by the coefficient and subtract 1 from the exponent, plus 8. And here we have our equation for instantaneous changing velocity. So now we can say Vt is equal to 3t squared minus 12t plus 8. And we know that this automatically is taken out when finding the derivative. So now we move on to B. B says find the acceleration of the particle. And here we have the answer. I'm sorry, sometimes I have those problems. And so we move on to B. B says find the acceleration of the particle at any time t. Now acceleration is given by the equation A of t equals d squared t over t squared. Now what does this mean? This means that we're finding the second derivative of the position equation. So we have already found the first derivative, so we need to find the derivative of this equation right here. Sorry for my little mistake here. There's a dt squared. D squared t over dt squared, which is also equal to ds, which is also equal to dv over dt. And we can relate this to our first velocity equation, because this means that this is the derivative of the velocity equation, or the second derivative of the position equation. So here we have, this is equal to at is equal to, once again we use the derivative laws, the power rule as it's called, 6t minus 12. And there we have it, our acceleration equation, which is the second derivative of the position equation and the first derivative of our velocity equation. Thank you.